right, welcome back. This is 4.2 Covalent Bonding. In your textbook, it's going to be pages 236 to 253. And in your workbook, it's going to be 64 through 68. This is not going to concentrate on naming of covalent molecules. We covered that in 4.1. I'm going to review that just a bit, but mainly this is going to be talking about the different geometric shapes that covalent molecules can take. So examples of covalent molecules are CO2, CF4, NO, and CO. Now remember that covalent molecules are two nonmetals bonded together. Okay, so if we look at carbon and oxygen, those are both nonmetals. Carbon and fluorine are both nonmetals. Now remember, on the periodic table, nonmetals are on this side of the stair-step line. Okay, so two nonmetals, that's what we're talking about here. All right, so covalent bonding is a bond between two or more nonmetals where valence electrons are shared. That's the key there, shared. They're shared to create a bond to meet the octet rule. When we talk about covalent bonding, for example, let's take water, H2O. We're going to look at lines. Okay, so these lines right here that connect the hydrogens to the oxygens, these are shared electrons between oxygen and hydrogen, okay, that create this bond. And so we represent that with a straight line like this. A straight line between two elements is what we call a bond, and this is made up of one electron from oxygen and one electron from hydrogen. So two electrons. So each line is two electrons. All right, and so remember, when we're naming, we use prefixes. So one is mono, two di, three tri, four tetra, penta, hexa, hepta, octa, nona, deca. So remember those. All right, so for example, this first one would be the only time we don't use a prefix, remember, is on the first element. So this is going to be carbon dioxide, carbon tetra fluoride, nitrogen monoxide, it's this one, carbon monoxide, diphosphorus pentoxide, tetrasulfur octachloride, nitrogen trichloride, boron trihydride. All right, so each one of those is named. So when you see a name, then it's going to tell you what the formula is, and then you can find out what shape, what geometric shape it is, which we're going to learn here in just a minute. So sharing of electrons, what happens when electrons are shared? So here we have the most simple example of this that we can have. We have two hydrogen atoms. Now remember, hydrogen has a nucleus and it has one electron in that shell. So we have these two hydrogens that when they get very close to each other are going to share those electrons that they have. Hydrogen wants to have two electrons in its outer shell for that outer shell to be full. And that's what hydrogen strives for. That's what any element on the periodic table strives for, is to have a full outer shell. Since hydrogen only has that one shell, it only has two electrons in that shell. So when these two hydrogens bond together covalently, they share those two electrons. So the hydrogen here on the right, the nucleus thinks that it has these two electrons. Okay. And the hydrogen on the left here this nucleus thinks it also has 2 electrons because those electrons are being shared. So this N2 is going to have a stable configuration because each one of those atoms thinks that its valence shell is full. So that's the idea behind covalent bonding. All right, so we have a technique that we use to figure out geometric shapes, and that technique is called NOS, and that's an acronym. It stands for N is the needed electrons for an octet. For that element to have a full, octet means a full valence shell. And for every element on the periodic table, that's going to be 8. So that's where they get the word octet. There's only one exception to that, and that is hydrogen. Hydrogen, since it only has one orbital and only 2 electrons can fit in that first orbital or first shell, then it only needs 2. But every other element on the periodic table is an octet, which means 8. The A in NOS stands for the actual valence electrons. And remember, we get the valence electrons by looking to see what group the element is in. For example, lithium is in group 1, so it has 1 valence electron. Magnesium is in group 2, so it has 2 valence electrons. So you have to look at your periodic table. And the S in NOS stands for shared electrons. And I'm going to show you in just a moment how to figure out how many are shared. So when we do geometry, we're also going to use the Honc rule, H-O-N-C. And the Honc rule says that hydrogen will get 1 bond, oxygen will get 2, nitrogen will get 3, and carbon will get 4 bonds. So just write that down, make sure that you remember the Honc rule. All right, so there's 5 geometric shapes that we're going to have to learn for this section on covalent bonding. And these are what are called Vsepr shapes. Valence, shell, electron, pair repulsion is the theory. So V stands for valence, S is shell, E is electron. All right, so we're only going to look at the valence shell electrons. Okay, electrons come in pairs. That means 2 electrons, either 2 electrons that aren't bonded to another between 2 elements, and we'll signify that or symbolize that with 2 dots, or the 2 electrons that are holding 2 elements together, and in that case, we'll symbolize that with a straight line. But these are always in pairs, 2 electrons. So remember, this bond is 2 electrons. And then repulsion. When electrons get close to each other and there's more than 2 of them, they repel each other. Actually, when they're close to each other like this, they also repel. If you remember when we're talking about electron configuration, 1 electron will spin in this direction, and then 1 electron will spin in this direction. So they spin in opposite directions. So that's how they repel. But when one pair of electrons gets close to another pair of electrons, then they start pushing against each other and repelling in opposite directions. We'll see more of that when we get into the actual shape name. So valence shell, electron, pair repulsion, Vsepr is the theory that we're going to be talking about. So let's go ahead and get all this erased so I can give you the names of those. All right, so the names of the 5 shapes are going to be linear, bent, trigonal, planar. Okay, and remember from geometry, planar means flat. Trigonal, pyramidal, and tetrahedral. Okay, so if we remember, the prefix tri means 3. So in both of these, you're going to have a center atom and 3 other atoms are going to be attached to it. Okay, tetra means 4. So you're going to have a center atom and then 4 elements are going to be attached to it. Okay, and on these two, linear and bent, the name doesn't help you here, but on linear and bent, you have 2 things attached to a center atom. So on all of these, we're going to have one element that's going to be in the center, and then things attached to that center. Linear and bent, 2 things attached. Trigonal planar and pyramidal, 3 things attached. And tetrahedral, 4 things attached. Okay. All right. So let's look at our first example. We're going to use carbon dioxide as our first example. So the way we do this NOS method is we take carbon dioxide like this, and we write it with a right angle. And we'll put an N, an A, and an S. And then what I'll do is I'll take carbon dioxide and I'll write out each element that's in carbon dioxide. So carbon dioxide has carbon and 2 oxygens. And then on one side, I will write how many are needed for a full octet. And on the other side, I'm going to write how many it actually has. Let's make these equal signs so we don't confuse those with bonds. All right, so let's look at carbon. Carbon needs how many electrons to have a full outer shell? The answer to that is going to be 8, because in the outer shell of carbon, this is the nucleus. The outer shell of carbon right now has 4 valence electrons. So that shell is not full. If that shell is going to be full, we would have to have 8 there to satisfy the octet rule. So that's 8. Now remember what I said a moment ago. Every element except for hydrogen needs to have 8 electrons to have a full valence shell. So oxygen needs 8, and that oxygen needs 8. So if we're going to have all the electrons that we need for every one of those elements to have a full valence shell, we're going to need 24 electrons. Okay, so that's where you get the N for NOS. A, now how many does carbon actually have? Well, if we look on the periodic table, we'll see carbon is in group 4. So that means it has, 14. So the last number of 14 would be 4. So that's 4 valence shell electrons. Oxygen, we look on the periodic table, we see is in group 16. So that has 6 valence electrons. So the actual number, we add these up, the actual number of electrons that they have here are 16. So we need 24. We have 16, so we're going to have to share some electrons. That's what S means, shared. How many shared electrons? Well, in order to get the number of shared electrons, you're just going to subtract these 2 numbers. All right, so if we take 24 and we subtract 16 from that, we're going to get 8. 8 electrons that are going to be shared. Now, if we go back to your notes 5 minutes ago, how do we symbolize shared electrons? We symbolize that with a line between 2 elements, and each one of those lines is 2 electrons. So we need to find out how many bonds this molecule is going to make. So in order to do that, we'll take this 8 and divide by 2. 8 divided by 2 is 4. So this is a little recipe that tells you how to draw this. So we're going to have 4 bonds, 4 lines in this molecule. We also need to know how many electron dots, unbonded electrons that we're going to have. And we get that by subtracting these bottom 2 numbers. So 16 minus 8 equals 8. So that tells us how many electrons that we're going to have. So we have a recipe for drawing this element. All right, so write this down. The rules for drawing elements. The first rule is if you have carbon in your molecule, that always goes in the center. Carbon always goes in the center. The second rule is, for the most part, if you don't have carbon, then it's going to be the element that's least electronegative besides hydrogen. The least electronegative besides hydrogen. So remember, on electronegativity, fluorine on the periodic table is the most electronegative. So as we move to the left on the periodic table, it gets lower and lower electronegativity. Okay, so the least electronegative is going to go in the center besides hydrogen. So here we do have carbon, so that's going to go in the center. So we have carbon. And what's attached to the carbon? There's two oxygens. So you want to space those out as equally as you can. So if we have two things that we're spacing out, it's going to be spaced out 180 degrees, one on each side. So we're going to put the two oxygens on each side like that. Then we're going to have 4 bonds. So we're going to distribute those evenly. 1, 2, 3, 4. 4 bonds. Now we're going to check for octets. So if we look at carbon here, and we look at the number of electrons that are attached to carbon, there's 2 electrons in each bond. So if we look at that, there's 2, 4, 6, 8 electrons that are already attached to carbon. Carbon cannot have more than 8. 8 is the number that carbon wants to have. So now we're going to go out to the oxygens. Well, this oxygen only sees these 2 bonds. That's 4 electrons. But we need 8. So that's where these come in. So in order to make oxygen have a full octet, we're going to have to add unbonded electrons. Actually, we're going to have to add 4 on this side. So we have 4 unbonded electrons. We have 4 electrons that are taken up in the lines between carbon and oxygen. So that's 8 for that oxygen. We've used 4 of these. So we have 4 electrons left over. We have an oxygen on this side. So we're going to add, 8 electrons on that side. So each oxygen has 8. Now we're going to look at this. We have 2 things attached to the center. So we have only 2 options that the shape of this could be, linear or bent. Now the trick is, since there are no unbonded electrons on this center carbon here, no unbonded electrons, this is going to be called linear. Because if we had unbonded electrons on this center, for example, if we had 2 electrons like that, these electrons would push on these bonds here and bend them downwards, and that would make this bent instead of linear. But since we don't have those, this molecule can set as a linear molecule. Okay, let's do another example, H2O. Now I'm going to go a little bit faster on this one since you know what we're doing. Okay, so in H2O we have 2 H's and an oxygen. Okay, how many electrons does hydrogen need to have a full shell? Well, since hydrogen only has 1 shell, it only needs 2. So that needs 2. Oxygen's going to need 8. So 8, 9, 10, 11, 12. We're going to need 12 electrons. Hydrogen actually has 1, and oxygen actually has 6. So 6 plus 2 is 8. Subtract those, that gives you 4. We divide that by 2. That's going to give us 2 bonds. Okay, and then 8 minus 4 is 4 electrons. So we have 2 bonds and 4 electrons. Okay, so what's going to go in the center here? Well, we don't have carbon, so we have to look at the least electronegative element besides hydrogen. Well, there's only one thing besides hydrogen, so that's going to be oxygen's going to go in the center. We have 2 hydrogens, so we're going to space those out equally. We have 2 bonds, 1, 2, We have 4 electrons that we have to use. So we're going to start in the center and work our way out. So this oxygen here sees 2 in that bond and 2 in that bond. So that's only 4. So we're going to have to make it have 8. So in order to do that, we do 5, 6, 7, 8. All right, so hydrogen, let's check hydrogen just to make sure we don't need those electrons for hydrogen. Hydrogen only wants to see 2 electrons. Remember, it only has that one shell. So it sees 2 electrons in that bond and 2 in that bond. So the hydrogens are okay. So here we have a molecule that has electrons on the center atom. Remember what I said just a moment ago. These electrons here are going to push downwards on that bond. These electrons are going to repel and push downwards on that bond. We have all of this space down here that's not being used by anything. So what happens is, since those electrons are being pushed in that bond, it's going to push that bond downwards. So instead of setting flat, it's going to push these downwards like that. So these 2 bonds don't want to get close to each other, but these 2 electrons that are up here on top are pushing this down, so we have to make it pretty much equal distance between all these. So it's going to be pushing them down into this geometric shape, and this geometric shape is called, it's pretty obvious, bent, because we only have 2 things attached to the center. Okay, so let's look at another example. We have BF3, and I want you to write this down. This is an exception to the octet rule. Boron only needs 6 electrons. So anytime you have boron as one of your elements, instead of it being 8, for some reason boron only needs to have 6. Okay, so let's write our NOS. So we have boron, we have 3 fluorines. Okay, boron, I just said, needs 6. And then the fluorines need 8. So 8 times 3 is 24. So we're going to need 30 electrons here. Okay, look at your periodic table. Boron actually has 3. Fluorine actually has 7. So 7 times 3 is 21, plus 3 is 24. Okay, so subtract those 2. 30 minus 24 is 6. Divide that by 2, and we're going to get 3 bonds. Okay? And then how many electrons? Well, 24 minus 6 is going to be 18. So we need 18 unbonded electrons. Okay, so I'm going to erase this 3 bonds here. Give me some room. I'm going to write it down here. All right, so what's going to go in the center? Well, between boron and fluorine, boron is the least electronegative, so it's going to go in the center. We're going to space our fluorines out equally. So it's something like this. We have 3 bonds, so we have 3 lines. Now we have 18 electrons. We're going to start in the center with boron. Remember, boron only needs 6, so it sees 2, 4, 6. So the bonds that are holding the fluorines on satisfies boron. Well, if I look at this fluorine only sees 2 electrons in this bond, but it wants to see 8. So 2, 3, 4, 5, 6, 7, 8. So I have to add 6 electrons there. And I have to do that with this fluorine and this fluorine. So I added 6 to each one of those 3. So 6 times 3 is 18. So I've used all of my electrons. So here we have the shape. Now, this is either trigonal planar or trigonal pyramidal. How do you tell the difference? Well, you look to see if there's any unbonded electrons on the center. See, we don't see any dots on this boron that's in the center. So it's not going to push that up into a pyramid. It's going to be able to lay flat. So this is going to be trigonal planar, because there's no electrons on that center atom to push those bonds downwards and pop it up into a pyramid shape. Trigonal planar. All right, and then we have here CF4. NOS. We have a C, and then we have 4 Fs. Okay, carbon needs 8, fluorine needs 8. Okay, so 8 times 5 is 40. Carbon actually has 4. Fluorines actually have 7. So 7 and 7 is 14, right? 14 and 14 is 28. Plus 4 is 32. All right, so subtract those two. 40 minus 32 is 8. Divide by 2, and that's going to give us 4 bonds. Now we have 32 minus 8. It's going to be 24. So we have 24 electrons. So what's going to go in the center? The least electronegative. Oh, we have carbon. Carbon always goes in the center. Okay, we're going to space fluorines out equally. So we have 4. We have 4 bonds that we're going to put in. So 4 lines. Carbon, we're going to check now. Carbon sees 2, 4, 6, 8. So carbon is fine, but each fluorine only sees 2, 3, 4, 5, 6, 7, 8, 3, 4, 5, 6, 7, 8, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8. So each fluorine got 6 dots. 6 times 4 is 24. We used all of our dots. So here we have a center atom with 4 things attached. So this is going to be tetrahedral for the shape. So that's as simple as it is. I do want to show you one example here that has a trigonal pyramidal. So if we look at pH 3, all right, so we have 3 hydrogens. So phosphorus needs 8, 2, 2, and 2. Okay, phosphorus actually has 5, 1, 1, 1. All right, so 8, 9, 10, 11, 12, 13, 14, 5, 6, 7, 8. Okay, so 14 minus 8, 6, divided by 2 is equal to 3 bonds. Okay, and then 8 minus 6 is 2 electrons. So phosphorus is going to go in the center. We have hydrogens spaced equally around, 3 bonds, so 3 lines. We have 2 electrons. Well, hydrogen only needs 2 electrons. So we have 2 electrons for each hydrogen that are taken up in the bond. Phosphorus needs 8 though. Phosphorus only needs 6. So we're going to have to put this extra pair, 2 electrons on the center. Now, since the electrons are on the center, that pushes that into a pyramid shape. So this is going to be trigonal pyramidal on the shape there. So you only need to know those 5 shapes. So let's look at what actually is happening with the electrons. So this is where the Lewis dot structure comes in, and this is how the book teaches it. The book does not show you NOS. So I'm going to show you what's going on here with these electrons and the Lewis dot structures. Oops, oxygen only has 6. So 2, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so what happens is these 2 electrons here are going to share. So I'm going to draw a line there. And then this electron is going to share with this electron, and it's going to flip down to make a bond here. Okay. And then these 2 electrons are going to share. These 2 electrons here are going to flip up to make a bond here. Okay, so that carbon can have 8 electrons around it. And then so I can get rid of these 2 electrons. Make this smaller. I can get rid of these electrons because we made those into a bond. We made these electrons into a bond, so I can get rid of those. Okay. And then we see here that we have 4 electrons on each of the outside of the oxygens here. See 4 electrons there and 4 electrons there. So I'm just going to erase those and just rearrange them a little so they look like they're in pairs. So 1, 2, 3, 4, 1, 2, 3, 4. And if we look back at our carbon dioxide that we drew earlier using NOS, we see we have the exact same shape. Okay. So the book doesn't teach you NOS. It's a trick that I learned from my chemistry teacher. It works every single time. So we get the same shape, but in the book and on tests, like if you were to take AP chemistry or if you were to look in the book, it's going to show the movement of electrons, how they form these bonds, and that's what it's going to show you, what I just showed you there. But for tests that I give you, I'm just going to ask you the shape, and you can do that by using the NOS method, and it works every time. All right, so that's it. So make sure that you like and subscribe. Slap that like button right across the face. Click subscribe, and then click that bell so you'll be notified when I put up new videos, and so you can get it either from YouTube or from my Canvas. All right.